What do California and Turkey have in common? Two regions, thousands of kilometers apart, yet both rest on restless cracks, or continents move sideways instead of colliding. From the San Andreas in California to the North Anatolian in Turkey, these immense fractures reveal how the Earth's crust drifts, twists, and reshapes itself over time. Welcome to Earth Diary, where we uncover the hidden forces that shape our planet. Don't forget to subscribe and watch till the end to see how transformed plate boundaries work, with real-world examples that connect California and Turkey. Stretching over 1,200 kilometers, slicing through mountains, deserts, and even city suburbs, this is the San Andreas Fault, a scar marking where the Pacific and North American plates grind past each other. It's one of Earth's most studied geological features, a slow-motion collision of immense plates that occasionally releases its tension in powerful earthquakes. But this story doesn't belong to California alone. Across the globe, Turkey's North Anatolian Fault tells a strikingly similar story of sideways motion and seismic power. Both faults are part of a special class of tectonic boundaries, known as transform plate boundaries. These boundaries reshape continents through gradual, sideways movement, and few illustrate this better than the San Andreas and North Anatolian faults. Let's explore how these two mighty systems continue to mold both landscapes. The San Andreas Fault marks the boundary between the Pacific Plate to the west and the North American Plate to the east. Here, the Pacific Plate drifts northwest, while the North American Plate moves southeast, at roughly 50 millimeters per year. This sideways sliding defines a right-lateral strike-slip fault, meaning if you stand on one side, the opposite side moves to your right. The San Andreas formed about 28 to 30 million years ago, when the subduction of the ancient Farallon Plate beneath California stopped. What replaced it was a transform boundary, connecting the East Pacific Rise with the Cascadia subduction zone farther north. This means the San Andreas doesn't create or consume crust, it simply accommodates lateral or horizontal shearing motion, conserving Earth's crustal material, while connecting two very different plate boundaries. Over millions of years, this motion has rearranged California. Major cities like San Diego, Los Angeles, and Big Sur lie on the Pacific Plate side of the fault, while San Francisco, Sacramento, and the Sierra Nevada are on the North American Plate side. Granitic rocks identical to those in Yosemite have been displaced hundreds of kilometers north along the fault. This sideways motion continually reshapes California's landscape. It creates linear valleys, long, straight depressions that trace the fault's path, like those in the Carrizo Plain, and offset rivers, where streams are shifted sideways as the land moves, leaving their channels visibly misaligned. It also forms basins, low-lying areas where the crust stretches and sinks, such as the Salton Sea, which occupies one of the most active sections of the fault zone. The fault system itself is broad and complex, containing parallel strands like the Hayward, Calaveras, and San Jacinto faults, all sharing the stress. The transform boundary is a critical feature in understanding the tectonic setting of the western United States. But the movement isn't smooth. Rocks along the boundary often lock under immense pressure, and when that stress is suddenly released, it produces powerful earthquakes. In 1906, a rupture along nearly 480 kilometers of the San Andreas devastated San Francisco. Later, the 1989 Loma Prieta earthquake proved that this fault remains active and dangerous. Its next major rupture, the feared Big One, is considered inevitable. Geologically, the San Andreas Fault is the archetypal continental transform boundary, a vivid example of horizontal shear, shaping the Earth's crust without volcanism or mountain building. Across continents, in northern Turkey, lies another spectacular transform system, the North Anatolian Fault. Stretching 1,200 to 1,500 kilometers, it mirrors the San Andreas in both length and right-lateral strike-slip motion. The NAF separates the Anatolian microplate, a continental block squeezed westward, from the Eurasian plate to the north, while being compressed by the Arabian plate from the southeast. Since Anatolia can't move downward or upward, it shifts sideways instead, a movement known as escape tectonics. The North Anatolian Fault takes up this motion, letting the land slowly slide westward, between the Eurasian and Arabian plates. Like the San Andreas, the North Anatolian Fault is a conservative boundary. It moves sections of the crust sideways, without creating or destroying any of it, simply shifting the land laterally, while keeping the overall crustal volume the same. The North Anatolian Fault displays striking geological features. It creates pull-apart basins, where the crust stretches apart by sideways motion, like the Erzincan Basin in the east, and the Marmara Sea Basin near Istanbul. Near the Sea of Marmara, the fault splits into several connected strands, forming a broad zone where the crust both stretches and sinks, one of Turkey's most active tectonic regions. It's a clear example of transtensional deformation, where sideways motion mixes with stretching, creates sinking basins. The North Anatolian Fault also includes both stretching and compressing zones, showing that continental transform faults are often much more complex and three-dimensional than simple straight fault lines. The NAF's earthquake history is also remarkable. It has produced a chain of major quakes, migrating westward like a row of dominoes: Erzincan in 1939, Bolu in 1944, and finally Izmit in 1999, a 7.6 magnitude disaster that killed over 17,000 people. The pattern of ruptures shows that stress is gradually moving toward Istanbul, which lies dangerously close to the fault's next likely rupture zone, beneath the Sea of Marmara. The North Anatolian Fault shows how continental transform systems mix sideways motion, compression, and extension, creating complex structures and powerful earthquakes. Now, let's step back and see how the San Andreas and North Anatolian faults fit into the bigger picture, the worldwide system of transform plate boundaries. Transform faults are vital connectors in the global plate tectonic network. They link divergent plates spreading ridges to convergent plate subduction zones, maintaining balance as plates move around the planet. Many transform boundaries lie in the oceans, offsetting mid-ocean ridges in zigzag patterns, as seen along the Mid-Atlantic Ridge and East Pacific Rise. But when transform faults form on continents, like the San Andreas and North Anatolian, their impact is far more visible and human. These transform boundaries cut across continents, forming striking landforms. They show that the ground beneath us is not static, it's part of a vast, interconnected machine, driven by deep earth processes. The San Andreas and the North Anatolian Faults, two distant lines on a map. Yet both tell the same story. That our planet's crust is alive, shifting, and sculpted by invisible forces deep below. Each slip, each quake, and each scar across the landscape is a reminder that we live on a restless, ever-changing Earth. If you found this video helpful, don't forget to like, subscribe, and explore more stories about how our planet moves beneath our feet.